Hello, my name is Edward Talmage. I'm an assistant professor of computer science at Bucknell University, and I'd like to discuss my work with my student Dempsey on efficient queues, particularly distributed implementations of queues, looking for space efficiency while maintaining good time performance. So the goal here is to take a data type, in this case queues, and implement that on a message passing system in an efficient manner. So typically that means time, but we're also in this work particularly interested in space efficiency. And what we have is that the notion of relaxation, where we take a data type and alter it in a particular way, enables more space efficiency and keeps time efficiency that had been previously shown to be possible through relaxation. So starting with some background definitions, when I talk about data type, an abstract data type, this is the interface that a data type requires. So what operations can you invoke? And then what behaviors will those operations have? So just the abstract means not implementation details, just what's the behavior. We talk about the behavior in terms of invocation responses. If I invoke with this particular argument, what response can I get back? What's valid behavior for the data type? Then we're looking specifically at relaxed data types. In this case, a relaxed queue data type. Relaxation, we take this interface specification and we say we're going to allow some extra behaviors that would not typically be correct behaviors. This is particularly interesting and useful when what happens is we allow multiple possible return values for the same invocation. And we'll get into why that's useful a little bit later. But that non-determinism, or multiple correct behaviors, can give us an edge in getting good efficiency out of these systems. And of course, there are many, many relaxations. We're just going to focus on one as a proof of concept that yes, a relaxation of a data type can increase the possible performance. And that particular relaxation we're going to consider is the out-of-order relaxation. So for a queue, if we're going to relax the D queue, it turns out not to be helpful to relax the N queue because it can be implemented quickly already. So we still have the same operations as usual. An N queue, which takes one argument, X, has no return value indicated by the dash. D queue doesn't take an argument, but it does return one value. And then a sequence of NQ and DQ instances is legal if each DQ is returning not the oldest argument that has not already been DQ'd, of an NQ that has not already been DQ'd, but one of the K oldest, where K is the relaxation parameter. So the larger K is, the more relaxed the data type, the more possible return values there are for a DQ. And if there are fewer than K elements in the queue, then we allow this returning the special bottom symbol for an empty queue. Note that that's possible even if there are a few elements in the queue, just not K. So pictorially, what does this look like? So initially, if the queue is empty, so 4 out of order here, so K, our parameter K is 4, then the first 4 values would be illegal. There are no values, so we can return bottom. That's the only thing. If we NQ something, well, then there's now one value we could return, but we could still return bottom because there are fewer than K elements. As we continue to NQ, once we have K elements, then we're going to get one of these if we run a DQ. For the sake of the example, we'll go ahead and NQ a few more elements. And so these are all in the queue. A traditional unrelaxed DQ would always return 1 if I DQ at this point, but a relaxed DQ can return 1, 2, 3, or 4. So it might return 1, that's fine. And then the set of elements that are legal to return shifts down because it's the oldest 4 elements. And if I DQ again, I could get 2 or perhaps 3. But once I get 3, note that 6 is now illegal to DQ because it's the 4 that are still in the queue, 2, 4, 5, and 6. And this may continue. I could get 6 next, I could get 5 next, and so on. So this is a relaxation of a DQ where instead of returning the single oldest element currently in the queue, it can return one of the K, in this case 4 oldest elements in the queue. So that is the type of non-determinism, or multiple possible legal return values for a given state. So why is this useful? Well, we're trying to provide a particular behavior to a user. So in userland, we're used to using data types. We call these functions, they behave in a certain way, give us these responses. We're used to this kind of interface. But our actual system is a message passing system where there are lots of messages going between different processes in the system, and they can cross each other in time and location, and it can be very hard to keep track of them. So we want to let programmers that are accustomed to doing, interact with their data the way they're used to, and hide the complexity of passing messages back and forth between many different processes. So we're trying to build this abstraction layer, and relaxation is going to let us do that more efficiently. So model details, n will be our number of processes. We're going to use a partially synchronous model. So we have bounds on message delays. Each message takes at most d time, so that's maximum message delay. And then u is our uncertainty, so d minus u is the minimum time. And a message may take that any amount of real time in that interval between when it's sent and when it arrives. We assume that every process has its own clock that runs at the rate of real time. And these are approximately synchronized to 1 minus 1 over n times u, which, so as n gets large, then the error between two clocks approaches u. And then we set up our algorithm as an event handling algorithm, where events that can trigger behavior are operation invocations from the user, a message arriving from another process, and then we allow setting timers because we have local clocks. And so we say at this point, after this much time has elapsed, then I'm going to do something else. So we measure time complexity in terms of the message passing delays. We're not as interested in computation time because that's relatively small compared to the delay in passing a message between physically remote computers. So we know from past work that in an unrelaxed queue, where every DQ must return the oldest element, then an implementation takes d plus epsilon, so maximum message delay plus variance in clocks, time between when you invoke a DQ and when it can respond. So the longer your messages take, and then the slower your operations are. Previously, we showed that with the out-of-order k-relaxed DQ, we can, while the worst case time doesn't improve, the amortized time goes down by almost a factor of the relaxation per node. So k is the relaxation, k over n is basically how much relaxation can be applied to each node. So if there are k elements that the DQ can return, k over n is how many of those elements each process can have if we split them up evenly. And so for a significant amount of relaxation relative to the number of processes, not the amount of data, which is probably much larger, then our amortized time can decrease significantly below what is possible for an unrelaxed queue. So taking that, our work in this paper says relaxation can give us good time complexity, but both of those previous algorithms for unrelaxed and relaxed queues had every process keeping a copy of the entire queue. Very bad space complexity. Can we improve that? And can we improve that without losing the time improvements that relaxation gave us? And the answer is yes, we can. Though, I mean, we lose a little bit of time, but we can get rid of the massive redundancy in space complexity. Now, in practice, you probably want some replication. You don't want to remove all redundancy in your data storage. But for the sake of exploring the bounds of what's possible, we're going to go all the way down to no replication and show that that's still possible and efficient. And then if that's possible, then some replication should also be possible. So an overview of the algorithm. So we're building on the previous algorithm for relaxed queues. So we'll first talk about how that works at a high level, and then get into some of the things we add to enable space efficiency. So if we have several processes and an invocation arrives, so the user at process 0 says, I want to enqueue 10. Process 0 will announce that enqueue operation instance to all of the other processes. And because enqueue doesn't actually have to return a value, it can go ahead and respond to the user. So this is a very quick interaction is from the user's perspective. They invoke, and almost immediately they get a response back. In the background, the rest of the system continues to update its stored copies of the structure so that it has proper state. So these messages take some time. There's variance in how long they take. Once you receive a message about an invocation, you wait a predetermined amount of time to synchronize and make sure that you know about everything that's happened so far. And then after those timers expire, each process locally executes that invocation on their own copy of the queue. So everybody stores the 10. And these may happen at different real times at different processes, but we can have them all proceed through the invocations in the same order so that their states match. What we want to do now is take that idea, and instead of having a complete copy of the queue at every process, split it up. So we're going to do one thing towards that end, and then we're going to actually make another note on something we can do for the common case for time performance. So we're going to separate storage into those things that may be returned very quickly and those things that may not be returned for a while. So those oldest K elements in the queue may be returned at any time. They're legal for a DQ to return right away. All of the other elements, it's going to be some time before they can be returned because other DQs have to happen first. And so we can spread them out among the processes and say those cold storage elements, it's okay if it takes some time to access them because we're going to have some warning that they're going to become legal to return before they are actually going to be returned. And if we update that more quickly, then we can improve our common case where the time from when I DQ an element to when I have another element ready to DQ is reduced. And so these two types of storage, we take the idea that processes are going to claim elements legal to return. So the efficiency of the previous algorithm for relaxed queues was based on if there are K elements, we'll split those K elements up among the N processes. So each process gets K over N elements. And it can return those elements quickly because it has them already. When it receives a DQ, it knows that it has claimed this element. No one else will touch it. So it can return it right away without waiting. If it has no such elements, then it has to communicate with the other processes to determine which element it can return because it doesn't have an element that it knows no one else will return. So if we take those claimed elements and observe that once it's claimed, no other process will touch it, then we only need to store one copy of it at the process that's claiming that element. And that's where it needs to be to return, so that's efficient. All of the other elements in the cold storage, which we call the stored elements, those we just distribute in a round-robin fashion for load balancing. And it turns out that you could try to do something fancy and say, we're going to put one here and one over there, and who has the least, and try to figure that out. But that ends up being more communication and more computation and more delay. Whereas if you just do a round robin, then the worst case is minimized. If you know something about the load, then perhaps you could do some balancing with some statistics. But for now, we focused on just what is the worst case. And what this gives us is that each process holds roughly a 1 in n share of the total data that has been put into the queue. So we get an even distribution. So the idea is straightforward. Credit goes primarily to my undergrad research student, Dempsey, for hashing out the details of this idea. But then the work from this point on is just to make sure that the details work, that we can prove it's correct, that we can prove the complexity. So let's look a little more in detail at how this system actually works. So we go back to, here's the state of our queue. We have 10 elements. So we're going to rename the first K elements, the claimed elements, and the rest the stored. So claimed may be returned by DQ immediately. Stored will not be returned yet. We're going to assign each element to a process in round robin order. The claimed elements, as long as they're evenly distributed, the exact order doesn't matter. The stored we do need to have in round robin order. And then we distribute them so that we have only one copy of each element stored at a single process. So we can see that process 0 has claimed element 1, and that's ready to return, so it's in blue. And then 5 and 9 are stored for later. And process 0 may not return 5 and 9. There's no way to know who's going to need those elements at this time. Similarly, process 1 has 2 claimed and 6 and 10 stored for later. So now if we go through the same scenarios before, we get an NQ. We respond quickly. We tell everyone, hey, I'm trying to NQ 11. We have the same delays. And then when we get to the point where each process should execute that on their local copy, most of the processes will not actually do that. They'll not store the 11 because we only need to store 1 copy of it. And we're going to do that in round robin order. Process 0 got 9, process 1 got 10. So process 2 should get the next one. So processes 0, 1, and 3 do nothing here. Not technically nothing. We have to count how many instances there have been, modulo n. And that counting lets us figure out round robin who gets the next one. And we'll use it again when we do DQs. But just maintaining one single counter modulo n is vastly more efficient than maintaining an entire copy of the queue. Then when process 2 finishes its delay for synchronization, it will locally execute the NQ because it knows it's next. It's the next process to store, and it'll store element 11 in its local memory. Now, if we invoke a DQ, we'll announce that to everyone. The invoking process, because it has a claimed element, can return immediately without waiting for communication. We go through a similar procedure. We send the messages out. Once we receive a message about a new invocation, we wait a predetermined amount of time to synchronize. Then we locally execute that. So process 2 actually executes the DQ because it needs to remove 3 from its local copy. Process 1 does nothing. Process 3, when its timer finishes, will do nothing. Process 0 will note that it has the first stored element. So the first element stored for later here is 5. And so it will remove that from its long-term storage and send that to restock process 2's claimed elements. Now, this does increase delay, but note that this is all happening in the background. The DQ invocation has already received a response. So from the user's perspective, it was a very quick operation. In the background, process 0 will send element 5 back to process 2. In the meantime, process 3 will just count that there was another DQ. Process 2 will receive it, wait to synchronize, and then store 5, this new element, in its claimed queue. So now when process 2 gets another DQ, it'll be able to return 5 promptly. If there had been a DQ in between before 5 was placed in claimed at process 2, then process 2 would have had to wait and couldn't respond quickly. And so we have this differentiation between 2 different kinds of DQs. If a DQ arrives at a process that has a claimed element, then it can respond almost immediately. If it arrives at a process that has not claimed any elements because it's run out, then there's a delay while that process tells everyone I need an element and waits to receive one from whichever node has the appropriate element in storage. We don't want to just return the first stored element here because that may not be among the first K. If, for example, the first stored element was the 8 at process 3, we would want to get 5 or 6 first. So the slow DQ takes 2 message delays, but the fast DQ, which is most of the time, in this particular example, half the time, but if K is even larger, then it'll be predominantly the most common occurrence, will be just 1 clock skew to synchronize everything and make sure we maintain state. So this type of restocking, as soon as process 0 realizes that process 2 needs a new element because it has DQ'd, is what we refer to as aggressive restocking for the sake of the presentation. And so if you think back to the example of the out of order, every time you DQ an element, the next element in the queue that's past the first K becomes legal to return. And so every time we DQ, whoever has the stored element will remove that from stored and send it back to the DQing process as its new claimed element. And our round robin ordering is important because as we count DQs, we can keep track of who has the next element. And again, it's just an integer modulo n, so it doesn't take a lot of space to keep track of who's going to be returning that next restock element when. And what we have here is if I don't invoke too many DQs too fast at one process, because if I do that, if I invoke a bunch of DQs in a small time frame, I'll run out of claimed elements, and then I'll have a slow DQ to go get some more. But if I invoke one and wait a little bit and invoke another, a fairly normal load as opposed to all in a rush, then by the time I run out of claimed elements, that first DQ will have received a restock and I'll have more claimed elements. And if I never run out of claimed elements, then every individual DQ will be fast. So this is kind of the common case. If I'm not just trying to pull as much data out of the queue as possible at one particular node, then each instance will be quick and the rest of my computation is not delayed waiting for the queue. So then we get to our results, and they are what you would expect intuitively. So if T is the maximum number of elements in the queue at any one time, then each process just needs T over N space for its share of the stored elements. So if it runs out of claimed elements, if all processes are out of claimed elements, then all the elements are in storage and they're evenly distributed. So you get T over N plus maybe 1 if the number of elements is not evenly divisible by N. But then you may also have some claimed elements, but that's limited so that no process ever claims more than an even share of the K to keep the worst case low. Again, if you have external knowledge of the load and where that this process is going to have more DQs than that process, then you could adjust this so that the busier process can claim more elements, but we're just doing everything level here for the worst case analysis. The other way to think about this bound, the other way you could phrase it, is that at any time, only one process is storing a copy of each element, not counting message buffers, because we have to broadcast it to everyone, but then most processes will just discard that. And so in their storage where they're actually keeping elements, there's only one copy system-wide of each element at any time. Our time complexity, so our amortized time, because we have fast and slow DQs, we need amortized time to get a good picture of what's going on. 2D is the time here for our slow DQ that sends a message out and then receives the restock back before it can return. And then we divide by K over N because that's how many fast DQs we have. And then there's actually epsilon cost for each fast DQ, but then that cancels with the K over N. And it's actually K over N because we have K over N fast DQs plus 1 slow DQ. And so that's our denominator for how many DQs we have for how much total cost. And the important thing to note here is with a relatively small K, so 4 times the number of processes, this works out to be distinctly less than the D plus epsilon that was the best performance we could have with a non-relaxed queue. So taking our space complexity down from total number of elements times N, because every process kept a copy, down to just total number of elements, which is the minimum possible, we still have time complexity less than is possible without relaxation. The 2 here is in orange because with full replication, we had just the 1D plus U because we didn't have to wait for elements to be sent back as those restocks. But that small factor of 2 that's still divided by our K over N is some cost that we have to pay. And one thing to note is that other somewhat more complicated and more useful relaxations already have a 2D in their amortized cost. And so our hope as we continue working on this is that this result will not actually touch the time performance for those at all while reducing the amount of space required. So the conclusion is relaxing data types doesn't just give good time performance, it also gives good time performance even without replicating the data. And so future work would look at how much replication would be good, though that gets into fault tolerance, which we did not deal with in this version. But we know that we can have as little or as much replication as we want with minimal, at most a factor of 2, impact on time, and it's still more efficient than you can get without relaxation. And then we also have the note that it's really only the edge cases where you have a really heavy load at one process that even hits that high bound. And in a common case, every DQ will be very quick, which is again something you can't do without relaxation because if every DQ at every process is trying to get the same element, they're all going to need to communicate. There is no fast case. They're all slow. So there's a lot of future work that's possible. So we could take this work on space complexity and keep going, do the same thing with other relaxations, expand to other data types. One thing is to try to not have to send every element to every process and then have most of them discard that message. But if it would be nice if we could determine in advance which processes to send it to. Now, in general, I don't think that's knowable because we don't know what's happening elsewhere in the system until we receive messages. And so we have this kind of wait for more information, but then by the time you took your action, that information would be out of date, endless cycle. But we may be able to do some sort of approximate or statistical analysis. And if anyone's interested in collaborating with me on that, I would love more expertise in that area to get a maybe not quite as good spacebound, but still improved and not sending as many messages or as much data in messages. Another area, so this is kind of part of a larger framework that's trying to take use relaxation as a tool to make data type implementations more efficient. So past work showed they were time efficient. Here we're showing that we can get space efficiency to whatever degree we want. I'm currently working with another student on trying to get some fault tolerance in here, see if relaxation can help with that at all. And we'd like to reduce some of the synchrony assumptions. So we're in this fairly well-behaved, partially synchronous model with known bounds on things. What happens if it's asynchronous? And the goal of all this is to move towards real-world systems so that we could actually use these. And so there are a couple of avenues there. Direct fault tolerance, what happens if our assumptions on message time are wrong? How can we handle or tolerate those? But the goal would eventually to actually put these in real systems so that they don't have to wait as long to interact with their data. Because we've shown theoretically we've proven that you can have better performance. And so we'd like to see that actually happen. And again, I'd be happy to collaborate with anyone who's interested in building some of these into a system. I'd like to thank, again, Dempsey Wade, my co-author. He was an undergraduate student here at Bucknell who did a lot of work. This was largely his idea, and I did the framing and presentation. I'd also like to thank InQ, Jimmy Way, and Shane Sterrett, who are in my theory of computation class this semester and helped find some references for the final paper. If you have any questions, follow-ups, other ideas, please reach out to me at my Bucknell email. I'd be happy to discuss further. Thank you.